Okay, welcome again to Energy System Modeling, and this is lecture number 6. So today we're going to go through wind and solar power modeling rather. And the lecture will start again by pondering with the, by the way, let's see that I have my screen shared. Yeah, should be on. So the lecture will start on pondering again why the wind and solar power production are rather important. We'll briefly kind of go through what are the things to consider when you're doing household, city level or country level modeling. Mostly this is about gathering data. You have to be able to gather solar irradiation data and wind speed and directional data. And then some techniques about wind power modeling and solar power production modeling. So what is required when you are doing these? So again, the same picture that I've shown you before about the energy systems. There's the supply, storage, conversion, consumption, and the transmission. So this is part of the primary energy kind of palette that you have the solar and wind, and at the moment on a larger scale, in a global scale, they are somewhat significant in terms of absolute amounts. But for example, in Finland and some other countries, some other regions, they have a huge impact on the energy prices, for example. So the conversion, it's already happening in the solar and wind power plants. So in that sense, it doesn't have this traditional conversion part. So straight to the electricity grid or to the consumption. And by the way, related to solar power, I think it was Albert Einstein that got the Nobel Prize on explaining this principle related to the solar power. So valokemiallinen ilmiö. I'm not sure what that was in English, but either way. So it's been known over 100 years. I think it was something like 1904 that he got the prize. But yeah, I digress. So why do you want to model the solar and wind power production? It's essential for energy system planning nowadays. Grid stability, market optimization. You have to be able to know beforehand what's happening. So it's related to the site selection. So what site, for example, provides the best wind conditions, solar conditions, investment decisions, and predicting the renewable energy output related to this grid stability. And this variability related to these production systems, it's in the kind of center of this modeling. So you want to be able to know how fast the system power changes. So as we talked about last time, it was about the storage optimization also. So you have to be able to know the production to be able to optimize the storage systems. So to enhance economic feasibility, and of course for policymakers, how fast can we implement these kinds of sources to go towards the net zero system? And this is the picture that we've seen also before. So the amount of energy that you can produce or power you can produce with wind and solar, it's massive, especially with the solar panels. So as they are becoming cheaper and cheaper, it's becoming more and more tempting to use this solar power arrays. In Finland at the moment, actually, there's a bit of a saturation going with the wind and solar power since they're cannibalizing their own profitability. So whenever there's a lot of this renewable wind that doesn't have in our market system, when we only kind of make the biddings to the electricity system based on the marginal costs, or the operating costs, and wind and solar have really small operating costs, it means that it drives the electricity price close to zero. So then it cannibalizes its own profitability, and if there isn't going to be any kind of consumption for it, it's like the electrolyzers, then it seems that there's a bit of a saturation going on in Finland related to this. But either way, if we can kind of jumpstart the hydrogen economy and add the consumption of these cheaper energy sources, then it's going to be it's going to do good for this wind and solar power development. And I think the capacity in Finland at the moment was somewhere close to 9,000 megawatts. So at least it's over 8,500. And like 10 years back, nobody would have expected that. 10 years back, it was somewhere close to 1,500 or something like that. So it's almost 10 times, well, 5 times bigger at least. So by the way, now you have the Moodle assignment 2, and there was the question that you have to modify. It was considering Finland as an island related to electricity production. So there's no connections to other countries. So the question was, or the assignment was, that you have to add some capacity in there. And of course, you want to add solar and wind, but as you can see, in some cases, that's not going to be enough. So that makes you kind of wonder and ponder what is going to be the kind of flexible, dispatchable power source for it. It has been biomass, but nowadays they are using even nuclear power to kind of down-regulate, especially when you have too much wind and solar in the system. By the way, don't increase water power too much in Finland. We don't have the capability or the rivers anymore for that. So what to take into account when you're doing this household level modeling related to solar and energy? The focus is on individual solar panels and really small wind turbines. So you have to have a high spatial resolution. And usually when you're gathering this solar irradiation data, you have to get like as close to your household as possible, but there aren't too many measurement stations in Finland. Well, there are many, but they are most likely not close to your house. So you have to kind of take some kind of an average, for example, from different sources if you want to make really exact modeling. And it's usually this kind of a deterministic approach. So based on hourly or even sub-hourly weather data and historical production from the installed system. So that's a good thing if your, for example, neighbor has a solar panel, then you can ask, hey, can I see your production data? If that's possible, then you can kind of backtrack the irradiance data. And that's really essential when you're trying to determine the system profitability. Of course, then you have to take into account shadings for the panels, and there are different kinds of panels nowadays in a way, or the attachments of the panels in a way that if one of the panels is shaded by, for example, leaves from a tree, then the others are affected, or if they are using these modern ways to kind of connect the panels, then it doesn't affect that much. Microgrid considerations may include the battery storage and demand response to optimize self-consumption. So you have to have accurate data on consumption. You have to have accurate data on the weather conditions. So were it the wind or were it the solar irradiation, or whatever sources, you can take the Copernicus data is the first you're going to go to and see there's a the one grid in there is something like almost 30 kilometers. So it's average based on that. And then you're going to go to this Finnish Meteorological Institute site and see if there's any more kind of with the measurement data with higher resolution. Limited aggregation effects. So variability is high as production depends entirely on local conditions, and you have really small production systems. So this applies to it rather well. There are different kinds of commercial systems that you can use, or the softwares that you can use to model these. And there are a lot of these internet calculators that you can calculate the profitability of solar panels. But I would say that it's always better to go for, if your neighbor has the panels, then you get directly the irradiation data from there. So city level modeling involves multiple households and buildings. So there's the effect of aggregation. So spatial aggregation of multiple photovoltaics and wind installations. So in this instance, or in this case, for example, the Copernicus data sets come into play. So you can take really the averaged wind patterns or irradiation data. And then you have to take into account the grid kind of grid-related issues. So how much electricity can you transfer in the network? So that's actually one topic or one issue related to one of the master's theses I'm supervising, that a certain city wants to kind of inspect if there's going to be a lot more wind power in their area. Does it kind of fit into the transmission grid? So higher grid interactions. You have to be able to kind of see how it interacts, how the production interacts with the grid, and if there are some bottlenecks in the transfer. Weather variability across locations. So you have to apply more of these complex weather models to make the predictions, but in terms of the weather data aggregation, and if you aggregate the kind of the weather data, it seems that it smooths out the profiles. So if you don't have these kind of gushes of wind here and there, or if you have them, it usually means that on the other place, it's more kind of stable. So they are averaging the really sudden spikes in the production that are evident in the household level. So then you can start to combine these bottom-up models and top-down statistical methods. And then you have to have this GIS-based tools. So you have to have kind of some kind of a location data in there. And country level modeling. So that's what you are doing with the SpineOpt, and we are doing it at a really kind of rudimentary, crude level. And what you're using in there is you're using previous year's data. So what is the capacity factor? So the overall capacity factor of a country comes into play here. Since Finland is one price area, then it's easy to use the previous kind of data from Finland, the whole Finland's production. If it were scattered or shattered into multiple price areas, price zones, it would be a bit more difficult. But in this sense, Finland it's a rather easy country to model since it's only one price area. So large resource mappings, you can use satellite and meteorological data for the forecasting, grid interaction studies, balancing variability with demand, transmission constraints, storage options. So there seems to be some kind of a bottleneck forming in the north-south direction in Finland related to the grid that Fingrid is already aware and it's taking precautions related to that. But since this Pohjanmaa, what's that in English? Österbotnia. Pohjanmaa is building, so in the coastal area of Finland, they're building most of the wind power. And Helsinki, for example, is what they are doing with the CHP production. They are shutting down the CHP plants and the heat production is going to be electrified. So there's going to be a lot of these electric boilers and heat pumps. So that means that electricity consumption due to this heat production electrification is going to increase in Helsinki. So they are kind of in net demand, and Pohjanmaa, since there's a lot of excess wind power production, they would have to be able to transfer the electricity from there to Helsinki. So that's forming some sort of a bottleneck. But they are still not talking about this making any kind of multiple price zones in Finland. So stochastic and probability models, that's what you're using in here. And the temporal resolution can, well, you can make an hourly, as in your case, in the SpineOpt exercise, you're going to make hourly resolution, but you can range to multi-year simulation as well. And then there's the market and policy considerations. Yeah, so 8,000, well, it was at the end of year 2024, 8,358. So I guess 9.5 or the 8,500. So you can see there's a really steep trend upwards, but it is showing the signs of saturations or saturation rather. So there has to be some kind of a consumption for this in Finland that's going to arise. Most likely it's going to be related to this hydrogen production, for example. So there is variability in wind production. So I think this was from Fingrid, yeah, and Renewables Ninja, or only probably on Renewables Ninja, yeah, because they offer these kind of more accurate resolution than just the entire country. So you can select a certain point from Finland, or then you can select the entire country, and there you can see the capacity factor, so power production index from the maximum, how much is being produced. So you can see that in Pori region, there are a bit kind of steeper changes, but there's not too much difference in here. So since Finland has concentrated almost all of its wind power production to the western coastline, it means that the entire country is rather close to what's happening in, for example, in this instance, Pori. So the load duration curves are almost equal. But then if you go to the Germany, this is from the, was it the Tom Brown had the course from this energy system modeling. I've linked the lecture slides in here and you can find the course totally or completely online. So that's a really excellent course. So you want to check that out as well. So there's Berlin wind, Germany onshore wind, and Europe all wind. So you can start to see the effect of the aggregation in here. So the best thing of course, that would be that the renewables would kind of follow the load. But in essence, this is a good thing, that the wider the area, the more flat your load duration curve is going to be, because it means that it's going to be steady production. So you can see in Europe, there are no 0 hours. And in Finland, I'm guessing there are a few that have just really small amount of wind power in the electric network. But either way, we are also not facing too many 0 hours related to this wind production. So the more geographically distributed it is, the better. But what this needs is a strong transmission network. So if you don't have that, then this doesn't matter. About the Copernicus wind data. So you can go and download freely. You just have to register in the site. You can download it freely. So there's a lot of wind data available for most regions. I don't know what's the coverage. I didn't check it, but for example, Finland, it covers pretty much all Finland, so including land and ocean areas. High temporal resolution, so they provide hourly, 3 hourly, daily, or monthly time series. So this hourly is really nice. Of course, this Finnish Meteorological Institute provides, I'm guessing, it was maybe 10 minutes, so it's sub-hourly production as well. There are multiple wind variability or the variables in this Copernicus data. So there's, for example, this wind component. So it's like north, south, east, west component. So when you have both of those components, then you can also calculate the direction of the wind. So that's a really nice system. So you can get the total wind speed from here. So different height levels, 10 meters, 100 meters, for example, are usually provided. And that is something that you can utilize with typical wind turbines, because that's pretty close to the height of the nacelle. And this ERA 5 is something that you want to look for. It is in a somewhat tricky format. So, but now at the era of AI, I wouldn't say that's a problem. So let's go here. Okay. Let's see. Copernicus ERA 5. So hourly data. And from here you can make downloads, and you can see that for wind, you could, for example, take 100-meter U component and V component. So you need both of those to get the direction and the kind of mean wind speed. And for radiation, you can see there's like surface thermal radiation downwards. That would be something that you want. And you can select from all the years. So there's a lot of data. You can select, for example, which month. So this would be January. And then you can select all the dates and all the times. And then in here, if I don't recall wrong, Finland would have been 70, 59 in here, 32, and this was probably 19, according to AI at least. So then I would say that and use this one, but I would have to log in here, some login problems now. But then you submit the request, this API request, and it takes maybe 10 minutes, and then you can download it. And what you can do with it is, for example, this was completely made with Python, because in Python, it can also, they have a lot of these map related submodels. So you can just use the AI suggested mapping model in there. And so this, for example, was this Copernicus. Let's see what it gives us. So what I asked for it to do is, because I downloaded the file, so it looks something like in here, finlandwinddata.nc. So just ask AI that I want to kind of use the native resolution and make a plot of the wind speed. So calculate the wind speed, don't include the direction in here, just the mean speed, and then use this map to attach on top of it. So that's from Finland, and you can see that the wind speed, for example, in the northern areas at that point was rather high, and in the sea areas as well. So there's a lot of data freely available. You just have to know kind of how to utilize it. And what I did manage to do with the data, I asked AI to make me a program that extracted, because the grids in Tampere region, I think it was 28 kilometers times 13 kilometers. And I'm thinking that the grid, the further north you go, the narrower it gets. So that's why it doesn't have like 28 times 28 resolution. So what I did is I took the wind data from all of these points. So there was 25 points what I had. So I have 25 different wind speed time series. And then you can calculate the wind production if you were to have, so this is from 100 meters. So it means that the nacelle is at 100 meters. And then I gave all the wind power plants the diameter of 150 meters and efficiency of 0.4. And that's the basic equation to calculate the power. So there's the minimum and maximum powers on this area. And if you have a lot of wind power in there, if everything was concentrated into one point, that would mean that there would be really large variations in there. So wind speed varies quite a lot, in a sense that in this area you can have like 2 meters per second lower wind speed in one region than the other, and that means that there's going to be a lot of this power variation. But if you're going to aggregate it, then it makes the power variation much lower. So that's the derivative of the power in megawatts per hour. So if I average out the data from this power production, there's only 1.5 megawatts per hour changes. But if I don't average it out, it means that there is a lot more variability in there. And that's a good thing for the system, because it averages out the production. So whenever you want to make this kind of an accurate wind power forecast or production modeling rather, it means that you have to cover kind of the overall area that you want. And this Copernicus data is really suitable for that. We'll probably try to utilize that in the exercises as well. So when you're modeling these individual wind turbines, which is kind of like the first step when you're doing this wind power modeling, you want to know what affects to it. So there's this cut-in speed, rated wind speed, cut-out speed. So I, for example, didn't take into account in my calculations, those ones. But at that certain moment that I was inspecting, the wind speed was pretty much in this range, so from 4 to 20 meters per second. So there's the region 1 where it doesn't provide any power. Region 2, this isn't exactly how it works. This is the theoretical power curve, and then you would start rating it, and then there's going to be the cutout speed, usually 20 to 25 meters per second. In this power plant engineering course lectures, I usually show the video where this wind power plant starts to spin like crazy, and then the blades shatter at one point. So the shear stress is too much for it. So you have to kind of start regulating the power production, and then there's the cutout speed when a storm occurs. And you can do that by, for example, this active pitch control. So changing the angle of the blades. So that's the basic the power equation, and that would apply to this region 2. But it's not exactly all the time like this, so it isn't this steep and exponential. But that's a good baseline to utilize. Then, of course, you have this Weibull distribution, which kind of shows you what kind of probability density function your wind speeds have. So that is something that you can utilize if you have the wind speed data and you generate this Weibull distribution, and then you want to calculate next year or next day or something like that, then you can use this for this forecast. So there's the wind speed and shape parameter and scale parameter. And what it looks like is something like this. And I went ahead and downloaded wind speed data from Siilinкari, so Tampere. You can see Siilinкari from Näsinneula, for example. It's rather close to the shore. So in here, there's the time. So again, UTC if possible. By the way, in your spine opt work, Justinas Jasuinas gave you another time zone that you have to utilize. So be mindful of that. So there's the keskituulen nopeus, so average wind speed, and then there's also the direction. So the direction can be used to plot this windrows. And by the way, there isn't any kind of a sensible way of making windrows in Excel. I tried and I failed. So utilize Python for that. That's much easier, especially with the help of AI. But what we did with the probability density function before, we utilized it for, I think, power production or power consumption. So you have that tool in your toolbox. So what I can do is I can distribute the wind kind of into different boxes based on this lower level and upper level. And then you get the probability of wind, how probable it is that the wind blows in this between 5 and 6 meters. So then you get the probability density function points, and then there's the Weibull distribution. You can utilize either Excel's Weibull distribution, or then you can utilize the equation that I just showed. It gives you both give you the same answer. And then there's the least square error fitting method utilized in here. So I'm taking this point minus this point to the power of 2 and calculating the sum of it. So with this solver, I can say that the K parameter is 2.88 and lambda is here. So if I change this lambda, for example, to 3, you can see that it starts narrowing down the distribution. So that gives you the how kind of a narrow, sorry, I was supposed to change this one. Yeah. That was the mean wind speed. Yeah. Yeah, no, I think it was this one. Yeah. So these both affect to the how narrow the distribution is. And you can kind of backtrack or backwards calculate based on the distribution that you have. If you have a certain time span, then you have the original wind speed. Then you give some random probability, and based on that, you can calculate with the Weibull distribution what is going to be your wind speed at a certain moment. So that is a good tool for making this kind of probability-based forecasts. And in here, you can see different kind of Weibull distributions. And of course, the ones that are more inclined towards higher wind speeds are going to be better for power production. And in here, you can see there's this V90 grid streamer, that's a wind turbine type, and you can see the power curve. It starts rating its power already in here, and in here it kind of flatlines until it drops down to 0 in 25. So that's the power curve. But a good estimation would be that you use the basic cut-in speed. So after 5 or after 4 meters per second, it's going to give me power based on the power curve that or the production equation that I showed you. And then in here, it starts rating it. So one thing, if you are making this wind power modeling and you only have wind speed at really low altitudes, for example, 10 meters, there's a way of making the scaling. So you have this kind of a simple exponential scaling equation that you can utilize that is somewhat accurate to some extent. There's this wind shear exponent that you have to kind of determine based on what kind of a terrain type do you have. You have smooth surfaces, for example, water surfaces, if it's open country, if it's forest. And if you have one measurement point in here at 10 meters, it's 10, at the height of 10 meters in here, it's 10 meters per second. So 10 and 10. So based on the exponent, it's going to be a bit more steep upwards if you have 0.1, so smooth surface, or if you have forest, it means that to reach 10 meters per second at 10 meters height, you would have to have a lot more wind upwards. So that is a good tool if you only have limited data from that area. So this is really good for those kinds of household level and maybe city level modeling. So it's just about, scaling up the wind in here. So if I were to draw these ones, so I have the Weibull based and then there's the higher altitude model. I think there was something wrong in that now because it didn't seem right, but this is the basic concept. One more thing you have to be able to kind of extract, and that's in the Copernicus data. As I said, they have wind speed in east-south, east-west direction and north-south direction. So you have the directional component. And this wind rose is something that you can kind of graphically show this probability where the wind is blowing. So it shows the frequency of or the percentage of winds blowing from each direction. And it typically has this kind of a circular shape with these sectors pointing out at each direction. So in this case, the probability for the southwest wind would be the highest. So they are really useful when you're doing this wind power modeling, especially when you are taking into account these wake effects. So that is an essential tool. And for example, you can also make this kind of a data based on this Finnish Meteorological Institute. So there's the wind speed, and what I've done in here, I've divided these again into boxes. I've seen that if something is between here, so it's the northern wind. So little less than 360 and little above 360. And the next one, north, northeast, northeast, east, northeast, and so forth. So different boxes, and then you calculate the probability based on how much data you have in there. So again, for example, you might want to use Python for this windrows. It's rather easy to get this kind of a plot based on the probabilities. So either you give the wind data and ask it to calculate it based on that, or just directly give the probability numbers for these ones. So it's really useful in taking into account these wake models. So for example, this Jensen wake model. In this course, we're not going to be going into details on this, but you have to be able to kind of notice that this kind of an effect occurs when you have multiple wind turbines. So that's a wind turbine in here, and the wind is blowing from left to right. And what it generates, it's generating a wake that is affecting to the average wind speed in there. So it means that the wind speed on the trail end of the wake is going to be lower. So it's going to affect to the next turbines. For example, there's A, B, and C turbines. So B is going to affect the C turbine, and A is going to affect to this C turbine. And there's analytical expressions that you can calculate this wake effect. But nowadays, they're also doing this with CFD modeling. So that's a lot more accurate. But for this layout optimization, because you want to do optimization, you have multiple wind turbines here and there, then you want to have analytical functions for that. So it just means that you're going to move this, since your windrows tells that this would be a really dominant direction, the white arrow in here, then you want to move the wind turbine from here to there. But again, when the wind moves, then it's already again on the way. So based on the most dominant wind direction, you are going to arrange the wind turbines in a way that the system provides the most production. And this is really kind of essential nowadays, because you can see in here, that's 5 kilometers. This is in Lestijärvi. So that's 5 kilometers. So there's maybe 500 meters, 1/10 of that, not sure. It may be even closer. So those wind turbines are really close together. And the other kind of coin of this equation would be, how much cable do you need? So you need to be able to distribute the wind turbines in a way that the wind, based on the wind rows, the direction, and also the wind speed, it would provide the optimal production. Of course, that would be that you would scatter it all around and you wouldn't have any kind of wake effects, none whatsoever. But then you would have a lot of cable that you have to draw. So that's the optimization problem. That's Lestijärvi, Central Ostrobothnia, Pohjanmaa. So this is going to be total capacity of, close to, I think it's a bit higher than that. There were more turbines in some sources, so close to 500 megawatts either way. So what you could do now, when you have the Copernicus data, and then you can have these coordinates of these systems, then you, together with AI, utilize this wind rows that you can get on based on the Copernicus data, and start seeing that if this actually is an optimal kind of configuration for this wind farm. 650 million euros. And if it produces 1.3 terawatt hours of electricity, and that's something that you could calculate, and you could see that if I move this wind turbine from here to here, we could have gotten this many million euros more. So that's this kind of a wind farm layout optimization is essential related to these. So solar power generation in Finland. The Fingrid gives you this total solar power capacity, but that's an estimate because they're not all connected to the grid in power plants. It's scattered all over. So they have to estimate it. Estimated the installed capacity by using installation statistics published annually by Finnish Energy Authority, Energiavirasto, that it receives from the distribution system operators. So it's somewhat vague, but seems to be rather accurate. So what's happened from 2020 to 2025, the installed capacity has, is it quintupled? So it's over 5 times what it used to be. And it starts to show in the production. And that's the yearly production. So during summer, it's high, but in the winter, it's near zero. But in a sense, that's a rather good complement for the wind power production. Since usually during the winter times, the wind power is at its highest. At least one of the reasons is because the air is more dense. But yeah, there's a really upwards growing trend, and the power plants are getting rather large. So this is just only a part of the this Kalanti. So let's see that from the map. You can see that there isn't everything installed in there, but I'm going to take Google Maps out and let's go to Kalanti. This is really nice when you can use these short excursions. So I think it was Uusikaupunki, Kalanti, and you can see it from here. So there's one site, there's going to be another, and you can see there's construction happening in here. And I'm guessing they are utilizing also some areas from here and here. And you can see that Google Map starts to kind of parse these satellite images together. Or I don't know if it's satellite, but either way. So this is going to be some 2,000 megawatt peak. So it means that the peak power when what the panels are rated for. So maximum 2006 megawatts. Once operational, it's expected to be the largest solar power plant in Finland. And 380,000 high capacity bifacial solar modules. So bifacial meaning that it can also produce electricity from the other side. So since there's reflection, it takes even less space. It's even more efficient. Or not more efficient, but it's more efficient in kind of utilizing the irradiation. So annual energy production exceeds 200 gigawatts. So from here you can see 200 megawatts and 200 gigawatt hours. So there you can calculate the capacity factor. So it's 10 or 12% maybe. So that's what's going on with the building projects. It's been a lot of those larger scale solar farms have been built. And for example, in Lempäälä, we saw that there was this battery energy storage right next to it, so to balance out the power production. So solar power production modeling, this is a pickle because there's a lot of things you have to take into account, and it's a lot of trigonometry. Because when you have a solar panel, sorry, but this is not going to show in Zoom. This is my solar panel. Hold your horses. So this is my solar panel. And if the sun starts shining, so of course you want to face it south. There are ways to tilt the panel in this way, in this way, in this way. So there are these following panels as well. But you want to get as much direct irradiation into here as possible. So based on the longitude and latitude, your sun kind of makes this kind of a bounce up. So there's this azimuth angle. So from the south, how far it is from the zero from the south. So it goes from here to there. And then there's the elevation angle. So how high it rises from the horizon. So that's the kind of opposite to zenith angle. So zenith angle tells you how far it is from the being really horizontal upwards. So what comes to the panel is this global, what you want to take into account is this global horizontal irradiance. And this is kind of a misleading. It's not horizontal because it's coming, well, it means that how much is coming to this horizontal kind of area on the surface. Direct normal irradiance, so how much is coming directly to the area that you're inspecting. If it's tilted, it's more. If it's horizontal, it's less. And diffuse horizontal irradiance, so that's something that's scattered from the clouds, for example. And then there's also the reflected radiation. So the albedo of the ground affects this one as well. And then what you want to calculate, if you have, for example, this global horizontal irradiance, and then you have this diffuse horizontal irradiance, you can calculate the DNI, so direct normal irradiance. So this is a lot of trigonometry, as I said. So how do you measure these? This is something that my kind of knowledge is really limited on, but this pyranometer. So there's this measurement device that you can use to measure this GHI or DHI, so this global horizontal irradiation or the diffuse radiation. So you can make a shadow on top of it. So that's the diffuse radiation and this GHI. And then there's the direct normal irradiance that you can kind of track the solar position, and whatever comes to it, that's normal to it. And what I did in Excel, then I made an kind of exercise on how to calculate these. So there are multiple sources that you can see the how to calculate, for example, solar declination. It's related to the fact that the globe is tilted. So if my head is the sun and the globe starts spinning around it, if it's sideways like this, it's a different angle than in here. So the solar declination affects to it. So you can calculate the solar declination, and what it should give you is something like this. So was it 23 point something degrees tilted? So based on what day of the year it is, the solar declination changes. Then your azimuth. This isn't really the exact way of calculating it, but it's rather close. So what it means that the day changes in here. So the sun goes from there to there, and again from there to there. So it makes this kind of a zigzag line. And then you can calculate the zenith. So how far away are you from the being horizontal. So in the winter time, you are much further away from horizontal level. And if we were to zoom in on here, so let's put, for example, 100 in here, you can see that there's daily variation, seasonal variation and daily variation. But this is pretty much all trigonometry. And Python, for example, offers you these kinds of what's it called, these libraries that you can calculate, these submodels that you can calculate these freely. So you don't have to necessarily do this. So the altitude angle is that matters. You want the altitude angle, and then you want the azimuth. So how it follows the east-west motion. And in here, if I put the altitude angle in Tampere region, it's something like this. So the sun starts climbing up to the horizon even more and more. So whenever you're doing this really kind of localized, not country level, localized, household level, or even city level, area level modeling prediction, this is what you have to utilize. And what you get based on that is the angle of incidence and the cosine of it. So that means how much of the radiation is kind of directly coming into the system. So if I decrease the angle of the system or the tilt, if I increase the tilt, you start seeing that more and more bigger proportion of the radiation starts hitting the solar panel. But then you can do an overkill. You can go to 60, and you notice that during the summertime, it starts climbing even higher than it should. I guess in Finland, it was somewhere close to 50 in Tampere region where the maximum production occurs. So that's why you want to tilt those panels in that way. This solar power production modeling also, you can utilize either this measured data, which is always, I think, better, because that offers you a way of avoiding making these kind of cloud models and utilizing this clear sky model. But what the clear sky model, it's maybe good for your understanding. So what it shows you is the amount of radiation that would come into this horizontal surface. So it only depends on the solar zenith angle. So how far away on the horizon the system is. And usually, this clear sky global horizontal irradiance is somewhere around 1011 or the 1100, but for Tampere region, it's a bit lower. And this is the clear sky model, and this is measurement from Tampere. This I don't know if it was from this ceiling cutting or where. But you can see the relation of this diffuse normal and this global horizontal irradiance in here. The global horizontal irradiance isn't actually the highest. And this is calculated based on the angle. So in here before, I gave you this, this equation in here. So what happened when I was trying to see this measurements from Ilmatieteen laitos, so Meteorological Institute, you can see that you have radiation observations and you have diffuse direct solar radiation and global radiation. But a lot of the data, so these would be the three that you need for the production modeling. But a lot of the data doesn't include this direct solar radiation. So that's why I had to calculate it. And it was based on the trigonometry again. So this red line is calculated based on the blue and the black ones. And it tends to be somewhat inaccurate when the sun is really close to the horizon. So that's why I had to cut a lot of those low angle values out. But yeah, that's those are the values that you can utilize in this local scale modeling. When you are going into larger scale models, then you might only use this GHI measurements, so global horizontal irradiance, and they are provided by this Copernicus again. So in Finland, I think it was somewhere around 28 kilometers times 13 kilometers. So that averages out rather well the effects of this cloud shading. So tilt and azimuth angles. So if that's facing south, how do you want to face the panel? And if that's the horizon, how do you want to face the panel in this way? That's the optimization problem. Usually when you're making household level systems, they are installed in the roof. So it's a fixed system. But if you can optimize these angles, it can increase the output by a lot. Usually 0 azimuth angle, so it's directly facing south. And there are solar tracking systems, so you can tilt the panel this way, you can tilt the panel this way, you can do it both ways, or just make this kind of a tilt on the right lower corner in here. So fixed, no tracking, single axis tracking, or dual axis tracking, so which is the full tracking. And in here you can see that the horizontal plate in here, just drop it on the ground, not much. Then there's this single axis tracking, this red and black, and full tracking, the blue one. So there is really a difference, but you want to optimize the costs, of course. So for example, this dual axis tracking, you could utilize it in concentrated solar power. So that's really essential when you're using these mirror systems. So it's more complex and expensive. So this single axis tracking could be utilized well in this utility scale solar farms. Even 25% in some cases better, based on what kind of a what is the variation in the azimuth, or rather the elevation angle. So for solar power production modeling, what I did again with this data that I got from this, I think this wasn't from Siilinкari, but it's from Middle Finland either way. So what it provided was this diffuse radiation mean and global radiation mean. And I filtered out the negative values from there, and then I calculated the direct solar radiation based on these two. So this is, measured values, filtered measured values, and then you calculate it. And I had an angle limiter. So it meant that if the sun is really close to the horizon, I'm not going to calculate the direct solar radiation, because then it would have been, in some cases, really high because of the inaccuracy due to the angle. So from there, you can calculate the overall production. So you have latitude and longitude, you have reflectance from the ground. And it seemed that this doesn't affect too much to the production as I calculated it. So we can put it to 0, and you can see the sum of the production it's rather low, low effect. So 0.2, some effect. So this would actually be the, so that's the total irradiation that comes in kilowatt hours per square meter. And then when I multiply it with the efficiency, it would produce that much. And then if I had 1.6 meter, which is the common panel size, it would be 460 kilowatt hours per square meter in a year. And that was close to, I think it was 500 to 700 that they said that in these regions it would be. So I'm fairly confident that this calculation could be somewhat correct at least. So this is from this measurement data. And the measurement data, what it does, it gives you all the variation. So if you have the variation in this production, then you can calculate the irradiance. So there's cloud cover, so you can calculate the production rather easily. I also went ahead and checked whether it matches the Copernicus data. So this is the Copernicus data. So this is the GHI. So they are, this is for May. And notice that with Finnish Meteorological Institute data, it's only from a single point. And this Copernicus data is from a wider area. So I'm not sure even if how they kind of conjure up those, if it's radar or this kind of satellite imaging, or how do they parse it together. But there seems to be some differences, and for kind of like localized system, I would use the Meteorological Institute, but of course for the larger scale system, you are going to use the Copernicus data. But I think the Copernicus only offered this global horizontal irradiance. I'm not too familiar with that. So it might be a bit more kind of vague estimation. So is there a kind of like correlation between the production and GHI? Because the GHI is usually what's being given to you. If I put this one to 0, you see that the correlation is rather strong. So GHI, what can be measured? If you just put the panel flat on the ground, it has a really nice correlation to the production of the system. But then when you start tilting it, then the geometry comes into play, and you get more light from the horizon when the sun rises. So then it's not as clear correlation anymore. So I think that was an interesting phenomenon in here. So if you only have this GHI, you can somewhat utilize it to calculate the production, but it's not going to be accurate. So what other things you can utilize? So large-scale solar systems with this aggregated production. You want to do the spatial averaging, so averaging irradiance data over the entire array with smooth or local variation. GHI, DHI give more stable estimate of the total power output. Then power curve modeling. So based on historical data, if you can get the data from your neighbor, what's the power production? Then you can kind of backwards calculate what's the solar irradiance and utilize that on your own panels. And then load matching. So these larger solar arrays, they aim to match power generation with local demand. So you have to have these battery energy storages in there. But that's something that we talked about last time, and you hopefully now have some idea how to calculate the power or the storage systems as well. An interesting thing is, of course, how these wind and solar power forecasting are made. So FinGrid maintains this kind of a comprehensive database containing the coordinates and capacities of all wind farms in Finland. So this information can be utilized in conjunction with the weather data. So you can retrieve localized weather forecasts specific to each wind farm's location, and then these are pretty much the tools that you utilize that I showed you to calculate the overall power. You have to have some information on the wind farm, for example, the average nacelle height and so forth. So actually, I'm going to show you the wind power curve in here. So there you can see the wind power generation, and then there's the day-ahead wind power forecast, continuously updated forecast. So the continuously updated should be a bit closer, and the day-ahead forecast, it's still rather close. In some instances, they differ quite a lot, but for example, this few days, and you can see there is a really steep change in here from 5,000 megawatts to almost zero, or 4,000 megawatts to almost zero. So the forecasts were able to predict that rather well. So it's not like it's going to be a surprise that tomorrow it's going to be, you know, low amount of wind. So of course the electricity producers are also monitoring these ones. So when to make the right kind of bidding for it. Also, Fingrid forecasts this solar power. So again, based on weather forecasts and estimates of installed photovoltaic capacity, derived from annual statistics provided by the Finnish Energy Authority. And I'm thinking that I'm not entirely sure, but I think it shows, so if we're going to put this järjestelmän tila, so the state of the power system, and let's go to heinäkuu. I'm guessing that's a bad date. Let's take another. Yeah. In some instances, well, in here you can see it. So there's this kind of step changes. Let's eliminate everything else than solar power. So that I think is because of the estimates. Yeah. So you can see that there are these kinds of step changes. So this isn't actually anything that you are directly measuring, but rather making an estimation even for this production curve. So it's rather hard to know how much we are producing. So local information is approximated based on the data that you get from the distribution grid operators, and that becomes the real-time forecast. And in the solar forecast, especially, well, the production amount is rather low compared to the total capacity in here on the upper part, the yellow curve. It's rather close to the, at least with this resolution. So this solar forecasting, I think it's a bit straightforward, at least a day ahead compared to this wind. So there's a lot, since the wind power is directly proportional to third power of the wind speed. So even a bit small fluctuation makes a huge change in the power curves. So for wind power forecasting, you use this database of wind farms, so all the locations. You use the weather forecasts. You use historical data. So the model compares forecast weather conditions with past production data to refine these predictions, and then real-time updates. If you have measured wind generation closer to the point of this forecast, then you utilize those to improve the accuracy. And that is essential in terms of maintaining the grid stability, because we don't have too wide of a land area. If we were to have wider land area, and especially where the wind power distributed in a wider land area, then the aggregation would make more of an effect. Solar power forecasting, installed capacity, weather forecasts, and production estimation. So real-time production data from small solar installations it's really limited. forecasts rely on weather models and statistical assumptions, and that is shown in the FinGrid data curves. And then I put some additional reading for you in here. So let's see if I can open these ones. And what was the I had one spelling error in here. Does anybody remember where it was? It would be nice to correct it. Usually here. So let's take, I'm not sure if the toy opened that, but it should be found really easily on this Google. Yeah. Solar power generation, intermittency, and aggregation. So you can see from the curves in here, they're talking about the averaging out of large land areas. And the same goes for this wind power. So wind power generation and aggregations, it's the same thing. Let's see if it opens from here. So from here, you can start to see how much the aggregation takes effect. So there's the load duration curves of certain areas. And the larger, well, there's the global wind production. And as you can see, it's rather flat. So if we had ideal transmission lines, then the problem would be solved. But the more local you get, the steeper the change in the load duration curve and the variability is going to be. And then a review on modern wind power generation forecasting technologies. So this was a really interesting article as well. Let's see if it opens up from here. Yeah. So there's a lot of these different forecasting methods that you can utilize. So physical methods, statistical, deep learning, hybrid model methods. So pretty much utilizing these neural networks and so forth. So if, and this was a really good article in a sense that there's a lot of sources, as you can see. So it goes through what it's a kind of a review article. So what these other researchers have been utilizing. So I put these in case of emergency. So if you need information related to these ones, this is real good reading, all of these articles. And of course, you can utilize AI to go these ones through. And tomorrow, most likely, I'm going to put you through on utilizing this Copernicus data, since this was, in my opinion, it was a bit hard to kind of to start using it, but once you got the hang of it, how to kind of decipher the files with the help of AI, then this especially was really nice that you can visualize the data really well. So there's the wind speed from Tampere, from the whole of the duration of 2024. So you can see even here during winter time, there are a bit higher. If I were to draw an average line, it would go something like this. So during summer, there's a little less wind speed, and that makes a little less wind production. And of course, the wind or the air density also affects to it. And then the maps that you can utilize, so you can make whole areas based on that. So this was really, really nice that you can make these rather easily. Yeah, so the devil is in the details in these ones. Whether you are making local solar or wind power forecasting or modeling, or if it's going to be nationwide, this Copernicus and Finnish Meteorological Institute provides you real quality data to kind of start making those models. Yeah, we were able to wrap this up a bit early today, but in case you have any questions, now we have the time for it. But if not, I can stop here.